You guys don't have questions because your state of readiness is more on the upper end of things, or is it because you still need some time between today and maybe Thursday for you to make a determination of whether you are ready for the assessment, your final assessment or not? When this session was meant for you to ask me any questions. Or maybe even I can ask questions if you guys don't have questions, to see how really ready you are for the final assessment.
Say on my side, can we maybe quickly go to November 2024, if possible? The very last question, question 7.
Is it on one of the question papers I shared, or is it a different question paper?
No, that's exactly one of the question papers that we shared.
Okay, let me just. You said November. Which trimester?
Paper. Let me just check quickly. You just said 21 November 2024.
Oh, November, so third trimester, 2024.
Yeah. Yes.
Oh, let me just look for it. You said question 7.
Question 7, sir.
All right. Let me just check if I do have it here. Let me just share my screen first. Can you guys see my shared screen?
Yes, sir.
Mm.
Okay,
Yes,
let's see. Okay, let me just check here. I'm not sure if I have it on my iPad. 2024, C3. I can't. Okay, I do have it. Oh, this kind of question, right?
That's exactly that one, sir. Yes.
All right. So remember, I said there's a 2-part video that isn't good enough to upload on my channel. I cover a question like this one.
Is it?
Yes, that is correct. So you can watch it on that video.
Okay.
I'm just not sure. I'm just not sure if it's exactly this question. Let me just check this video quickly. Okay. Okay, so it's not exactly the same question, but it is the same questions. So it's not this question, but it is a similar question.
Similar question.
Yes, similar question, meaningly, it has different values. So it's essentially the same question, but the magnitude of the quantities is different. For instance, the mass, the RAM of the shaping machine is on the one I'm going to send is 150 kilograms, whereas on this one it's 110. The concept that you follow in solving this question, or the approach that you take, is going to be the same. Right, I will send that in the group. In fact, let me do so now while I still remember. Sometimes I'm working with quite a few groups, and I promise all the groups something every day. So sometimes I forget to share some of the content with some of my groups if I don't do it right away. So I'm gonna send this in the group now. Like I said, it's a two-part video, so you can watch that, right, to familiarize yourselves with the approach that you take on such questions. Right, the video is pretty straightforward. Like all my videos, I explain everything there. But if after having watched the video, perhaps you can attempt this one, and then if you feel like maybe something is missing, maybe there's something you couldn't figure out from my video, then you can, of course, send me a text, and perhaps I can uh, redo this question in a manner that I can upload on my channel, where everything will be much clearer. Yeah.
Okay, thank you, sir.
All right. Did you look at? Yeah. Okay. I guess if even if you have the memo, if you don't understand how I got to something, you would need an explanation there. Is that what the problem is?
Exactly, say yeah. So
Okay. No.
I couldn't move. Yeah,
Okay. No, I get you.
it's basically that. Yeah.
Right. I explained everything regarding such problems. Right. If you look at the problems or exercises I did on my videos based on metal cutting machines, I did explain there that metal cutting machines depends on the kind of machine you are looking at. So each machine has a certain approach to it. Um, the the concept is more or less the same, because with metal cutting machines, you're still looking at essentially um, what is engineering principles. So engineering principles are the same, but how you apply them is based on the kind of machine you're looking at.
Okay.
Right. So when you look at the video, okay, I've just sent this video in the group. Just confirm if you got it. Yes, it is sent. Second example based on. All right. Have you received the video? Second example based on.
Just I'm just checking here on my side.
All right.
Yes,
So
sir.
Yes, sir, we got it.
it's
We got it.
yes,
Yes.
it's in our group. All right. So that
Yes, sir,
video,
we got it. Yes, sir.
yes, that video will explain everything in detail, right, regarding problems on shaping machines or such problems where you have a cutter and you have to, in having to calculate the cutting force, you essentially have to use what is this? You have to use, what is this thing? Conditions of equilibrium. Right. So everything is explained there. So make sure you watch that video. So after having watched the video, just tell me if the video is detailed enough for me not to re-record a video that will be good enough to upload on my channel. Yeah.
Yes, sir.
Right. Was this Andy Makina?
Yes, sir.
Is that all, Andy?
Yes, yeah. So far, say it is all. I just have to go through uh, the question papers and yeah, if I pick up or maybe I get hooked, maybe I will maybe just give a shout. Then
All right. Well, okay. No,
yeah,
understood. In your preparation, just make sure the content I sent last week, that you make sure that you go through it. Right.
yes,
So in everything that you do, make sure you do that one.
Yes, sir.
I hope I'm clear. All right.
Yes, sir. Um,
Yes, because it's probably the only out of all the exercises that I sent you, those are the only ones that I identified that I perhaps found interesting outside of the ones that we have done or that I have shared. So upon attempting the ones I sent last week, should be fine.
okay.
All
So
right.
that includes all these the question papers that you sent to us as well. Is that what you
Yes.
mean?
Yes.
Okay.
Yes. But if I was you, I'd first attempt the exercises that I sent last week, including the ones pertaining to module 1, 2, and 3.
Okay.
Yes.
There's a
All right. Also,
yeah.
remember last week I also shared the um, the four main graphs that you get under bearings. That is the only thing that we didn't really discuss as far as bearings. Those four graphs, or perhaps I did discuss them, but not in detail. That is why I sent you those videos because I. That is why I sent you those graphs. Was just to make sure that you go over them. Normally, if they are included in the final assessment, they are about 2 marks each. So there's four of them, which means there will be like what 8 marks. Eight
Mhm.
very easy marks. So you just need to know how to draw them. So you don't have to draw them exactly how they are on the pictures I sent you, but you know you just need to make it clear in terms of the proportion of the graphs that this kind of graph looks like this and it has these labels. So normally you get 1 mark for the drawing of the graph itself and then 1 mark for the labels, which is 2 marks.
Uh,
So make sure you know those graphs just in case you get to the assessment and boom, 8 marks is going towards those four graphs. It's pretty straightforward. And also, it's been a while since I've seen them in the exam, so
yes.
that's why I want you guys to keep an eye out for those because it's more than likely that we will see them in this assessment or maybe in the next one. Definitely this year, I'm certain we will see those graphs because we
Those
haven't seen
graphs.
them in a while.
Is it?
Yeah.
So the graphs you're talking about, is it the one that are sinusoidal or the like on the notes or something?
Second.
Or the ones is it the ones that are sinusoidal or the one
Yes.
that
Yes,
then
those
okay.
ones. Yes, exactly those ones. Let's just quickly go to the textbook. Mm, yes, but to answer your question, that is the graphs I'm referring to. See these graphs here. If you look at number 2 here, it's written mean loads. So those are the mean load graphs. There's linear, fluctuating, continuously fluctuating, as well as sinusoidal. There, these graphs. You see? So by when I say you don't necessarily need to draw them exactly how they've been drawn here, I mean, for instance, if you look at the linear fluctuating load, right, just have to draw the two axes, draw the zigzag lines, and then label F max and F min. Right, and then the fluctuating step load, you just have to draw something that looks like steps, right, and then you indicate that F and then perhaps the Fn. Right. No need to go crazy there. Similarly with the continuously fluctuating, you need to draw something that looks. So if you look at the continuously fluctuating and the sinusoidal, right, there is a good chance you might draw them the same. But if you look at them, right, if you look at them, the continuously fluctuating load graph, right, it is not constant, right? What is this thing? The way you draw.
Distortion.
Say
That
again?
distorted.
Yes, if you can if we can put it like that, right? You don't see like what is it? This is what I'm looking for. Um, what is this thing? What do you call this graph? That has an upper and lower limit. I forgot this word now. But if you look at the two graphs, the way they are drawn, there's a clear difference between the two, right? In terms of the consistency of the curve. What do you call this thing? Parabola. Yes.
Oh, the
If,
parabola.
yes, if you look at the sinusoidal fluctuating graph, it's parabolic in shape. Right? Whereas the continuously fluctuating, right, as much as there is a maximum or there is a turning point, right, the shape isn't quite parabolic, if you know what I mean. Right, so make sure there's a clear difference between the two. Right.
So you said you get how many marks for you get 1 mark for
1 mark for the graph itself, so 1 mark for
yes
drawing the graph correctly, and then 1 mark for the labels.
for the labels. Oh, okay.
Yes. Yeah, but in terms of the labels, right, just try to identify the most critical ones. There's no need to show everything. You just need to show the critical parts of the graph.
Okay.
Right. Out of all the modules, hydraulic systems normally carries the most marks, normally like 20 marks. And then what is this? Gear drives also carries a lot of marks. It's normally like 15 marks, more or less. It's normally about 15 marks. So you can get a lot of marks there as well. Precision measurement. Most of you struggle with precision measurement. I don't know why. It's probably the easiest. Precision measurement is probably the easiest because there isn't really a concept that we follow there. Right? Everything is mathematical, really.
I
It
think for
just
me,
it just
sir, sorry. I think for me, I think it got me to panic because when I look at the video, I could follow it.
Yeah.
But when I'm doing the question
Yeah.
papers,
Mm.
then I get you find out you kind of chose the wrong what do you call it? Your labelings are not really
Oh,
right,
okay, okay,
something
yeah,
like that. I think that's what the problem is. But I
yeah,
told myself that just gonna give it a try because in terms of the concept, I kind of get it.
yeah.
But when I got to do it myself, then that's where the problem comes. So it kills me penny, but I'm on leave from tomorrow. So I think I'm just gonna give it one more try before I ask questions so that at least I know exactly this is where my struggle. So I think that's the main problem for me.
Okay. Now with that one, mm, looking at, So normally I'm able to, like, based on past exam questions, normally I'm able to predict, if I can use that term. Perhaps not all the questions, but at least some of them, by looking at what was covered in the past exam papers. Now I'm saying that to say this. The question on precision measurement, where you have to label. I just forgot what this thing's called. I think this question was on the first assessment. Let's just go there quickly. Where you had to calculate some measurement X or H, and then you had to label. You had to label, yes, this kind of question. You see 1.2 here?
Yes, sir.
Yeah.
All right. So make sure you do this kind of question as well. Make sure you understand how to attempt this kind of question. Did we? What just happened? Can you guys still see my shared screen?
Yes, sir.
Yes, sir.
All right. I just want to check here if I should. Let me see. Okay, so I didn't. Right. So make sure that you practice this question as well, because this kind of question I haven't seen in a while as well. This kind of question. I wouldn't be surprised if you see it in your assessment, in your final assessment. Right. So make sure you practice when you practice tomorrow. Make sure that you practice this one as well. Precision measurement. Precision measurement is quite easy, because aside from ring gauges, which ring gauges I've tried to make easy for you as well. But aside from ring gauges, every other problem based on precision measurement, you essentially attempt the same.
Look,
Because
say, look, I think on my side, one of my problems is I would say it's more like time consuming, if I might put it that way, because now you have to take time to analyze the drawing self, yeah, before you then start maybe with the calculation, and then once you spend quite a lot of time there, and then you then start panicking now, yeah, because of you want to get to the end. Yeah, that's basically one of my problems when it comes to that. Yeah.
precision, okay.
Yes. Yeah.
Let me.
For example, if we look at that very first question, yes, yeah, I'm not sure if is there maybe a different way that you can approach it, and then maybe understand it and do it even quicker. Mm.
All right. Let me. I want to squash what you just said just now. I want to show you something to prove to you how easy precision measurement is. Okay, let's look at that first one. So this one first. Now looking at this question, right? Regardless of what exactly they'll be looking for here, when you get this question, I guarantee it. Whatever exactly it is that they're looking for, they might be looking for the diameter, they might be looking for some measurement here. It doesn't matter.
Yes, sir.
Either way, when you get such a question, first thing you do is you do this. Uh, so you do this. Remember that on precision measurement, right? The left hand side is equal to the right hand side,
Yes, sir.
right? So meaningly, even if you project that line to there, So this is what you have. Take that as A. The center is B. Now you know that seeing that you have two tangents, this tangent, they're meeting at this point. It means this point is a point of interest, meaning that you can call it C, right? Now, if you've labeled the left-hand side is equal to the right-hand side. So
Yes, sir.
if this point is a critical point, it means this point is a critical one as well. So meaning if that's C, call this D, that's E, that's F. First thing you do, right? Then you look at your question, you're looking for X. To get X, you must have A, you must have AB, you must have BC, you must have CD, you must have DE, you must have EF. Right? So looking at just that, you know that AB is the radius. So if
Yes,
AB
sir.
is the radius, it means EF is the radius. So you have AB and you have EF. What about BC? You know BC is equal to DE, so it means you just need to calculate one of those. Right? How do you calculate one of those? You already know the concept of two tangents meeting at a common point. That's a tangent, that's a tangent, they're meeting here. And if so, it means you can draw this triangle. Right? You label your triangle, maybe call this, say, call it G. Right? How do you get BC? You need to get this small angle here. Do you have this whole angle? Yes, you've been given
Yes,
that angle at 65 degrees. You know
yes,
that once you draw this line, right, from the center of the roller, right, from the center of the roller to the point where the two tangents meet, you know that this line separates these arcs into two equal halves,
yes, sir.
right? So if this is 65, it means this angle C is half of 65. So you have this
Yes,
angle, you have this side is the radius, so it means you can get BC. Once you get BC, it means you'll only need CD. How do you get CD? You know you have to draw the triangle, right? And you know that triangle is equal to this one,
yes, sir.
right? You have this side, it's 35, right? You have this angle or this one, right? Depending on which one you want to use, right? You know that this whole angle is 90 degrees. If that's 65, it means what is this?
That's 90 minus 65. That
Which
will
is
now take it to 35,
25.
25, yes.
Yes. So you have the angle. So you have the angle. You have the side. It means you can get that side, which
By
means
using,
get CD by using whichever what is whichever trig ratio is convenient.
okay, yeah.
Right. In this case, because the sides that are of interest, which is this one, which is the side you have, and that side, it means the sides that are of interest are the sides um, that exclude the hypotenuse. So which means the only trig ratio that you can use is tan.
Yes,
Just gonna depend which angle you're using. So if you're using this angle, so this will be the opposite side, this is the adjacent side. If you're using that angle, this side is the opposite side, that's the adjacent side. Either way, the only trig ratio to use is tan because you won't be using the hypotenuse.
yes,
All right. So my point here was, you see, we haven't even discussed. Remember, we haven't even discussed, or when we started with this, we didn't even look at what is it that we're looking for. Because it is
yes,
this kind of problem, you know that you have to project this, project that, and then the other points are pretty straightforward. Why? Because this point we know is where the two tangents meet, so that's a critical point. That's what is this? That's the radius, hence making this point critical as well. What you do on this side, you do on this side. Right? Similarly with this one.
sorry, said,
Uh-huh.
just before you go, just can you go back to that drawing? So meaning that now ultimately to get that distance, so that's gonna be now your two sides depending to whatever the 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 length is on the two triangles. It's gonna be 125 minus the sum of the two
Yes,
to get that middle
CD.
the yes at the CD.
Yes.
Okay.
Right. With precision measurement, right. Perhaps let me put it like this. Precision measurement, you look at what is it that you're looking for, or before you even look at what you're looking for, you look at the kind of problem you're looking at. Right. Based on this kind of problem, where are the critical points? First, identify the critical points. Right. On this kind of problem, the critical points are A, B, C, D, E, F. Those are the critical points. Right. Once you've identified the critical points, you then look at what is it that you're looking for. Here, we're looking for X. Right. X is this measurement. Right.
Yes.
What's the algebraic expression for X? So X, based on the critical points that you've already labeled, X
It's
is equal
AB. Yes, yeah.
to AB plus
It's
BC
BC.
plus DE, okay, plus CD plus DE
E.
plus EF.
Yes.
That's the algebraic expression. Then you ask yourself, which of these sides do you already have? We have AB and EF. Both of those are equal to the radius. So which means
Yes.
you can replace those with the radius. So essentially, from the first algebraic expression, now you have 2R plus
Yes.
BC plus CD plus DE. Right, so no longer have this. So you've eliminated some of the unknowns. Right, from AB plus EF to just 2R. Right, which of course in this case, because you have the diameter, right, it means you have 2R. Right, BC you can work out, you know that you have this triangle. So once you have BC, it means you have DE. So again, you've eliminated another unknown. Instead of BC plus DE, now you have 2 BC, because you know BC is equal to DE. Right? And then CD, you do not have CD, but you know how to get to it. Right? Like you said, to get CD, it will be the 125 minus 2 times the distance.
Yes.
Yes. You get your 7 marks. This is before you even start attempting the problem itself or start drafting your solution. But just doing these little things, right, that is half the problem done right there.
So that's just a quick question. Am I then required to redraw this and on the question paper to indicate all the like my calculation like A, B, B, C, or I can just maybe do it on a separate page and
You are not required. On an official basis, no, you are not required to redraw this. Right?
okay.
The reason why I suggest, I always suggest that you redraw this, is because just make it easy. It makes it easy to draft your solution. Right? To make things easier, you can redraw. You can do this on your question paper.
Yeah,
Right?
yeah, okay.
Right? If you look at this diagram, I obviously didn't draw it. Right? All I did was
Yeah,
label the critical points. So you can do the same.
okay.
Right? You can do the same. Right? When drafting your solution, but knowing that you have done this somewhere,
Yes, sir.
so as to not get lost with your solution.
Okay.
Right? Right. Any more questions on this one?
Sir,
Mm-hmm.
I have a question.
Yes.
Just so if you don't do the drawing, right, how is the examiner's gonna know that you're speaking about BC or AB? You know what I mean?
They will know. They
Okay.
remember
Okay.
your examiners or your markers. Yeah, they've been doing this for quite a while.
Mm.
They've been doing this for quite a while. So based on just your response, they will know if you have the correct response. They will know exactly where is it that you are referring.
Okay.
Yeah.
Because I
Precision
was
measurement.
also
Precision measurement
thinking about the
is straightforward.
Mhm.
I'll beat it just now. Precision measurement is pretty
Okay.
straightforward. It's very important because unlike with other modules, we, markers or examiners cannot really, carry forward mistakes, right? Because as the term suggests, precision measurement. It's very easy to mark because you're either right or wrong.
Mm.
It's unlike the other modules where in one question maybe you punch the code the calculator incorrectly, and then in the next question you need the answer that you got in the first one. So you find that they discuss that if that happens, then they carry forward the mistake. Right? It's unlike those, because with those you're just looking at understanding, not so much the values, if you know what I mean. But with precision measurement, we are looking for X, and there's only one way to get X. Right? It's not like they say maybe 1.1 calculate this, then 1.2 calculate this, and then 1.3 calculate X. What is incorrect responses cannot be carried forward. Hence, you're either right or wrong. So don't worry about that as far as precision measurement. Your examiners, yeah, don't worry about it.
Okay.
I think thanks for that. I think it's gonna eliminate the time that we spent, like the guys was commenting about, to try to get this in a picture. That so I think like you suggested that if we put this, like you make your pointers or your labelings on the question paper or something, because it's actually you're taking whatever that is on a question paper, you're putting it on the answer sheet for you to be able to. So I think that for me, I think that's gonna help us a lot in terms of time consuming.
Yeah.
That's correct.
That is correct. Yeah, so you don't have to redraw the whole thing. Right? You can just label it on the question paper and just draft your solution. Because there's no mark for, I don't know if you've looked at my marking guidelines. There's no marks allocated for the drawing itself. Absolutely none. Right? The reason why I even do it myself is for your convenience. Right? So that you are able to follow exactly what it is that I'm referring, because you're still learning, Right? Any more questions on this one? So my whole point here was that even before, right, you start drafting, right, there's little things that you can look out for, right, to help with your solution. And it really doesn't take much time doing this. Right? Similarly with this one, right, these kind of problems, it does not matter what it is that they are looking for. You see such a problem, this is what you do. You know this is what you'll have. You will have this right-angled triangle. Right? Draw the triangle. This is before even knowing what exactly they're looking for. They might be looking for that height h, right? So just like here, they might be looking for the height of the slip gauges, or sometimes they want you to calculate the diameter of the precision roller. Right? Either way, you are going to have this right angle triangle there. Right? And then also, in terms of which algebraic expression to express or to expect, right? You will have A here, that will be B, that will be C. Right? This is before you know exactly what they're looking for. And then perhaps you can call this one G. So make sure you don't call this one D, because you might confuse it with the diameter. So call this one G. All right? And then now you can look at what you're looking for. You're looking for the height H. Right? So what's the algebraic expression for the height H? Or which algebraic expression is H a part of? Right? And it's this one. It's always going to be this one. Right? If you look at this measurement here, right? So this is AC. So AC is equal to, right? So AC is equal to AB plus BC. Right, if you look at this, it's equal to AB plus BC. Right, you know AB is equal to the radius. Right, and then BC, you can use this right angle triangle to calculate. Right, and then what else is AC equal to? If you project AC to this side, right, AC is equal to H plus 50. So AC is also equal to H plus 50. Right, that means to get H, you must get AC, because in this case you're looking for H. Right, so H is a part of this algebraic expression, right, which means to get H, H is AC minus 50. So this tells you that to get H, you must get AC. How are you going to get AC? From this algebraic expression. Right, so you go back to this. This is AB plus BC, right? And then because we've already established that AB is equal to the radius, it means you've eliminated that unknown. So you know this, but you don't know BC, which means to get AC, you must get BC. Right, so how are you going to get BC? Using this triangle. Right, so using BCG, or you can say using triangle BCG, up to you. Right, you already know that angle. Right, if this is 60, then that's 60. Those angles are basically opposite.
Yeah, 30 degrees.
Right, now, of course, again here, the concept of two tangents meeting at a common point. You have this tangent, you have this tangent meeting here. It means you have this line that you draw from the center of the roller. Right, and that line always splits these arcs by half. So which means if this is 60, it means that's 30. Very simple. Right, and then how are you going to get BC? BC is the hypotenuse of this right angle triangle. Right, the angle that you have is here. The side that you have is that radius. Right, PG. So the side you have is this one, which is 30 degrees. I mean, the angle that you have is 30 degrees. The side you have is opposite the angle, which means because you're looking for the hypotenuse, the only thing that you use is sine. Yes. So sine, call this sine 30 is equal to opposite, which is the radius, over the hypotenuse, which is BC. Right, sine 30 is equal to half. So essentially half is equal to the radius, which is, so the diameter is 40 millimeters, which means the radius is 20 divided by BC. Right, now you cross multiply, which means BC is equal to 40 millimeters. Right, you have BC. If you have BC, you have this. You already have the radius. The radius is 20. 20 plus 40 is 60. You have AC. AC is 60. 60 minus 50 is 10. Straightforward. Similarly, right, I want to prove to you that the approach is going to be the same regardless of what it is that they're looking for. So say you have the height h, but you are now looking for the diameter of the roller. What is going to be the approach? The very same. The approach is going to be the very same. Right. So say now that h is 10. So h is 10 millimeters. So you have h. So again, you take the same approach. Right. These are your critical points as labeled. They won't change. They remain the same. But now, what are you looking for? You're looking for the diameter of the precision roller. Right. So again, you go back to this expression, A to C. A to C is equal to AB plus BC. AB is the radius. BC remains as BC. And then AC is also equal to H plus 50. But now H is 10. So that's 10. Which means AC is equal to 60 millimeters. Right. So you have AC, but you do not have the radius and you do not have BC. So which means to get the radius, you must figure out what BC is, or figure out a way to express BC in terms of the radius, so that in this expression, you only have one unknown. Right? Either way, you have to go back to this triangle. Going back to that triangle, so using BCG, right? We are looking for BC, right? We know we have this side as the radius. Our angle is 30 degrees. So you say sine 30 is equal to opposite side is the radius divided by BC, right? So obviously you still have two unknowns, but to eliminate this unknown, right, to eliminate BC, you have to express BC in terms of R. That way, when you substitute BC here, it will be in terms of R, hence you'll only have one unknown there. Right, sine theta is a half.
Sorry, sir.
Mhm.
I just got lost now where you said you have two unknowns. You have the R and the BC. Oh,
Yes,
yes, yeah. So I just now lost you now where you said you have to
express
substitute.
one,
Yeah, to express.
express
Yeah.
one in terms of the other.
Yes, yeah. Oh,
Right. Now look here, you have two unknowns. Right.
yes.
The only thing you can do here is to either say R is equal to whatever in terms of BC. So the left hand side will be in terms of BC, the right hand side will be in terms of R.
Okay.
Right. Either way, one of the sides or either of the sides will either be BC or R. But
Okay.
now, because you are looking for the radius and you've already established the algebraic expression where you can get R,
With the R. Okay.
which is this one, right?
Okay.
From this one you have AC, but you do not have BC, right? And then in trying to figure out what BC is equal to, BC is still an unknown. So the next best thing to do here is to make sure that you express BC here in terms of R, so that when you substitute it here, right, you will no longer have BC, but you will have a value that is in terms of R. So meaningly, so sine 30 we know is a half, so R over BC. Then you cross multiply. When you cross multiply, BC times 1 is BC equals to 2 times R, which is 2R. Now, if you look at BC, right, the left-hand side is in terms of BC. So BC is equal to 2R.
R. Okay.
So this is what I meant by
Oh,
expressing
okay.
BC
Okay,
in
sir.
terms of R.
Okay.
That way, when you substitute it back to that expression, AC is equal to um, R plus BC. Now, instead of BC, we know that BC is equal to 2R.
2R. Yes,
You
yeah.
can simply replace that with 2R. Right.
Okay.
This way, AC we know is 60, and then 3 plus R plus 2R is 3R. Right. Then you divide everything by 3. Right. What is 6 divided by 3? That's 20 millimeters, which means the diameter being equal to 2R is equal to 2 times 20, which is 40 millimeters. Now, if you look at the approach, it is exactly the same.
Hmm.
Right? Especially how you start your solution, it is exactly the same.
Hmm.
Right? So precision measurement, you just need to know exactly which problem you are dealing with. You just need to have practiced different problem or different exercises based on precision measurement. That way you will have established where to start. Right? And where to start is to identify critical points. Identify all your critical points and then look at what you're looking for. And then look at what it is that they're looking for. Either way, for that kind of problem, the approach will be the same.
Hmm. Okay.
I can do this for any kind of problem. It's based on precision measurement. Any.
Mm.
It's a matter of identifying the kind of problem.
Mm.
Yeah. Just watch my videos closely if you have to go back to my videos. Right, so once you figure this part out for precision measurement, it's an easy 15 marks. Very easy.
Mm. Mm.
Right. Are we okay here on this one?
I'll
Yes,
say
sir.
yes, sir.
Right. Right. So that was just my quick pointers on how to attempt problems in precision measurement. Right. There is another one that I want us to look at. Right. So this is a problem on epicyclic gears. So I just want you to tell me how to label this thing. We'll look at the schematic illustration, and I just want you to tell me how we can complete the first condition. Remember, I said the first condition is the most important one, right? And it's the first condition is the only one where the schematic illustration matters. After that, it doesn't really matter what, like the kind of epicyclic gear system we are looking at. Right, so that only matters for the first condition. Right, everything else after the first condition, right, you would approach the same, regardless of the kind of epicyclic gear system, be it a typical one or an atypical one. Right, remember how I said you must arrange your components. Right, the first two are based on the first condition. First condition speaks of the arm and the annulus. That's why I have these two components first, and how you arrange, or the next columns that follow, or the next components that follow, will be based on how the gears are measured. So because you have an annulus gear, the next gear would be the one that measures the annulus. The next one will be the one that measures with the. So the first one after the annulus will be the one that measures with the annulus, and then the one that follows is going to be the one that meshes with the gear that meshes with the annulus. Right. Now let's look at this epicyclic gear system or gear train. So you are given two perspectives, right, to make it easier for you to understand. Right. So obviously you have the annulus. The annulus is A. Right. You have the arm. The arm is arm E. Right. So you have arm E. So this is arm E. That's arm E. The annulus is gear A. So that's A. Now, which gear meshes with the annulus? Which gear meshes with the annulus here?
Gear D, sir?
Gear D. Yes, that is
Yes.
correct. That's gear D. Right. Even if you look at this perspective, right, The dotted lines, remember what the dotted lines means as far as engineering drawings, right? It means that component you cannot see from this perspective.
A hidden detail.
Yes, it's a hidden detail. Thank you. Right. So even from this perspective, you can see that the smallest gear in the system is the one that is meshing with the analyst, which is this gear. Right. So yes. So here, now before I write gear D, now you must take note that this is not a typical epicyclic gear train. Right. It is a compound epicyclic gear train. Why? Because some of the gears are fitted with the same shaft. Now we've identified or we've established that it's gear D that meshes with the analyst, but now gear D is fitted with the same shaft with gear C, which means gear D and C are rotating at the same rotational frequency, which means it doesn't make sense for those two gears to have separate columns, because we've already established that seeing that they are fitted with the same shaft, it means they are rotating at the same rotational frequency and rotating in the same direction. Which means when you write gear D here, because it's gear D that is meshing with gear A, you then say and what is that? C. Right, so gear D and C are going to be in the same column. Why? Because they are rotating at the same rotational frequency and rotating in the same direction. So to avoid having to confuse yourself of having a column for D and C and end up overlooking the fact that they are fitted with the same shaft, hence rotating at the same rotational frequency and in the same direction, to avoid that confusion, right, straight away you have them under the same column. Am I making sense here?
Yes, sir.
Yes, sir.
Right, so C and D or D and C are in the same column. Why? Because they are fitted with the same shaft, which means they are rotating at the same rotational frequency and rotating in the same direction. Right, now which gear follows after that? The gear that meshes with either gear C or D. Now in this case, it's gear C that meshes with gear B. Either way though, there isn't a column after this one that represents just C. Right, hence the column that follows this one is for gear B. B meshes with C. Right, so those are your gears. Right, now you look at the number of teeth. If you've been given the number of teeth, remember, to be able to complete this first condition, you need all the number of teeth of the gears. Right, so now you go to the number of teeth will either be given on the schematic diagram or they will be given in the statements. So in this case, they aren't given in the schematic illustration. So you go to the problem statements. It reads as follows: the episodic gear train shown in figure 3, consists of an analyst A having 100 teeth. So TA is equal to 100 number of teeth. Right. And sun gear B connected to the output shaft having 28 teeth. So gear B, so TB is 28 number of teeth and rotating at 140 radians per minute in a clockwise direction. The planetary gear D having 16 teeth. So gear D, that's TD, has 16 number of teeth. And gear C having 22. So TC is equal to 22 number of teeth. So we have all the number of teeth of the gears, which means we can complete the first condition. As first condition is contingent on you having all the number of teeth. All right, now let's complete the first condition. All right, you fix the arm is 0. You rotate the analyst for one direction clockwise. Analyst gear A is +1. Now, question is, how does that affect the rotational frequency and direction of rotation of gears D, C, and B? We already know
So,
D and C. Yes.
sorry, sir. The gear A, we said on that column +1.
Second.
The on gear A, sir, on that column we said look on the arm with we have 0, and then on gear A
Yeah.
we
Plus.
have a +1.
Yes.
I just
I'm
yeah.
reading the question.
Where is the +1 coming from, sir?
Okay.
If I may.
It's coming from this condition, right? For epicyclic gears, condition 1 and 2, right? They remain the same always. So, meaningly, the first condition will always be to fix the arm and to rotate the annulus by one revolution.
Oh, by one revolution. Okay.
Yes, by one revolution clockwise. So the positive stands for clockwise. The
Okay.
one stands for the number of revolutions.
Okay.
Right, hence the +1. Right. So
Okay,
this
sir.
and this come from the first condition.
Okay, sir.
Yeah. And then the question
Okay,
is,
sir.
how does this condition affect the rotational frequency as well as direction of rotation of gears D, C, and B? And the way you answer that is by following the three guidelines I gave you last week, right? Which are based on how you've arranged the components of the gears, you already know that this gear meshes with this one, right? Remember that any gear that meshes with the annulus tends to rotate in the same direction as the annulus. Now, bearing that in mind, you follow the three steps into completing this condition for gear D, right? So, first step is to establish the relationship between the two gears in mesh being D and A, right? Gears D and A. Right. First step is to establish the relationship. The relationship between them is that the their circumferential velocities are the same, which means mathematically nd times td is equal to what is this? Is equal to so a na times ta. That's the relationship between the two. Next step is to establish direction of rotation. We already know that the annulus, based on the first condition, is rotating clockwise, which means if the annulus is rotating clockwise, it means gear D is also rotating clockwise. Why? Because any gear that meshes with the annulus rotates in the same direction as the annulus. Are we clear there?
Yes, sir.
Yes, sir.
Right. Which means clearly the annulus is positive because it is rotating clockwise. Now, this one, right, will also be positive. Why? Because it is meshing with the annulus. Hence, it's going to rotate in the same direction as the annulus. So both directions are going to be positive for clockwise. Then third step is to solve for what you're looking for. We are looking for ND here. So you divide both sides by TD. That cancels. Therefore, ND is equal to NA times TA divided by TP. Not TP, TD. All right. This is TD. All right. Then now you substitute. So ND is equal to NA, which you already have. NA is equal to +1. So that's +1. And then TA is 100 divided by TD. TD is 16 teeth. So that's 16. And what is this equal to? What is 100 divided by 16?
6,25, sir.
Second?
6,25, sir.
6,25. Right. So when we fix the arm and rotate the analyst by 1 revolution clockwise, gear D rotates at 6,25 RPMs, which means, seeing that gear D is fitted with the same shaft as C, it means also gear C is going to rotate at 6,25 revs per minute in a clockwise direction. That is why it is important, or it is convenient, to have both of these gears under the same column. Otherwise, you might want to calculate the rotational frequency of C after having calculated the rotational frequency of D, which simply doesn't make sense. Am I clear?
Yes, sir.
Right. So now, to complete your first condition, you just have to complete the first condition for gear B. So again, you follow the 3 easy steps, which gear is meshing with gear B, gear C. What's the relationship between those two gears? They are in mesh, which means their circumferential velocities are the same. Mathematically, that means NB TB is equal to NC TC. Right. First step is to establish the relationship between the two, which is this here. This is the relationship between the two mathematically. So next, you establish direction of rotation. We've already established that gear C is rotating clockwise. Right. See, this is positive, which means it is rotating clockwise. Now, gear C and B are meshing with the outside true circumference, which means they are going to, or they are rotating in opposite directions. So if C is rotating clockwise, it means B is rotating anti-clockwise. So which means this one is negative. So you slap a negative sign there to show that gear B is rotating anti-clockwise based on these conditions. All right. So third and final step, you solve for what you're looking for. We are looking for NB. So you divide both sides by negative TB, thus making NB the subject of the formula. So that cancels, meaning NB is equal to NC TC divided by negative TB. Right. And then when you substitute that, you have NB, it is equal to NC, and then NC we know is equal to ND, which means it is equal to 6,25. So this is 6,25 times TC. TC is equal to 22 number of teeth. So this is 22. All of this divided by negative TB. And what is TB equal to? 28 number of teeth. So negative 28. And what is this equal to? What is the numerator? Second?
It's going to be negative 4.91
91.
and 11 if we want to make it 3 decimal.
Yes, always make it 3.
Yeah, make it 911.
Yeah. So negative 4,911. Right, and just like that, your first condition is done. Right, if you follow those 3 easy steps, this thing will be very easy for you. Very, very, very easy. Very easy. Just like precision measurement, this here is quite easy as well. You just need to know the steps to follow, or to know the approach, the best approach to follow. Right, now I want to show you something else here. Yeah, I want to show you something else. So let's complete the second condition. Second condition is you multiply the first condition by x, then you add y. X times 0 is 0. And you add y, that's equal to y. X times 1, x, add y, plus y. 6,25 times x is 6,25x, add y plus y. Negative 4,911 times x is negative 4,911x, then you add y, so plus y. That one is done. Now every other condition that follows here will be based on what has been asked. Like for instance here, you have 3.1 and 3.2, which means that it is likely that each of those questions, 3.1 and 3.2, is a condition on its own. So you look at 3.1, and then remember that to complete any other condition after the second one, you need three quantities. You need what you are looking for, and then you need two other assumptions. So as far as what is that you're looking for, you look at the question, calculate the speed and direction of the annulus. So you're looking for NA. So out of the three quantities you're looking for, you already identified one. That is what you're looking for. So next, now you need two assumptions. Calculate the speed and direction of annulus A if the arm E is fixed. So you have one of your assumptions. One of your assumptions is that the arm E is fixed, which means NE is equal to 0. Right? Then now you need one more. What is this? One more assumption. Now that assumption hasn't been given in the question, which means it's likely given in the statements or even shown on the, what is this thing? Or the schematic illustration. So if you look here, they say episodic gear train shown in figure 3 below consists of an annulus A having 100 teeth, sun gear B connected to the output shaft having 28 teeth and rotating at 140 revs per minute. So you've been told that this, right, gear B is fitted to the output shaft, which is rotating at 140 revs per minute in a clockwise direction, right? A planetary gear D having 16 teeth and C having 22 and mounted on the same set of axes, right? Now, if you look here in the statement, you are told 140 revs per minute clockwise. In the schematic illustration, you are given 120, right, for the same shaft. Right. In this case, you have to choose one. Obviously, there is a typo here. Right. Either the typo is this one or is this one. Either way, you have to choose one and stick with that one. Right. Your markers or examiners will take into account that the examiner made a mistake here. Hence, both solutions will be considered. So a solution for someone who used 120 and a solution for one that used 140. Right. So when if it happens that you see such a mistake, do not panic. Choose one, do it. Because if you leave it, if you identify a mistake and say the examiner made a mistake, I want to attempt this. Next thing, the markers discuss and decide to consider both solutions. So by both, I mean consider solutions for someone who used the 140 and consider the solution for someone who used the 120. If you decided to leave the question, you are out. So even when having identified mistakes, right, use your own discretion. Right, do not leave a question unanswered though, because you have no idea what the markers are going to agree on. Are we clear there?
Yes, sir.
Yes, sir.
Right. Either way, your other assumption can either be given in the schematic illustration or the problem statements. In this case, you are given in both. So that is to say that even if it is not given, one of the assumptions or two assumptions are not given in the statement, it might happen that they've been indicated on the schematic illustration. Right. For instance, here they said the arm is fixed, so they could point to the arm and write there fixed, which you can take as one of the assumptions. Right. And then, of course, the output shaft right, is 120 revs per minute. So if they didn't indicate clockwise, like for instance, had they not written this in a point statement, instead they just pointed at the output shaft, which is fitted to the sun gear B, and said it's 120 revs per minute, you take the fact that there is no negative sign there as that this is rotating clockwise. Did you hear that part?
Yes, sir.
Right. So for now, we are going to use the 140. But like I said, you could either use the 140 or the 120. So this is NB. This is the second assumption. NB is positive 140. Positive 140 because this NB is rotating clockwise. Right. And then of course you complete your third condition, and then you formulate equations by equating the second condition with the current condition. Right. So meaningly, for instance, here you have NE, that's 0. You have NA, which is what you're looking for. Right. There's nothing on D and C. You have something on B, which is positive 140. So in having to calculate NA, you then have to establish equations by equating second condition with the current condition. So you have y is equal to 0, x plus y is equal to NA, negative 4,911 x plus y is equal to 140. Then you solve those simultaneously to get NA. That one is pretty straightforward. Then to complete, because you have 3.2, right, and they want you to determine the speed and direction of one component, it means you're going to have a fourth condition. Fourth condition, you need three things. What you're looking for, two assumptions. Determine the speed and direction of arm E. So we've identified what we're looking for. We're looking for NE. Now we need two assumptions. Now the two assumptions, like I said, could either be in the question itself or embedded in the statements or on the schematic illustration, assuming the analysis A is fixed. So analysis A, so now the analysis is fixed. So NA is 0, which means as far as the second assumption, we are still going to use the assumption that's embedded in the statements or the schematic illustration. Now remember that you've already chosen 140 instead of 120. So you stick with that 140. So NB is equal to positive 140. Right. So here you're looking for NE, which is the arm. The analysis is 0. This is still positive 140. And then, of course, you know what's next here. You establish equations by equating second condition with the current condition. And then you solve simultaneously. Any questions? All right. In N5, you will find epicyclic gears there as well. The concept will be the same. You will still follow the very same guidelines that I'm teaching you right now. So make sure you remember these guidelines. They will serve you well, even in N5. Are we clear?
Yes, sir.
Any questions?
So far, so good. So
All right. In that case, perhaps let's look at the problem on. Okay, yeah. Belt drives. Now there is another video I'm going to send you on belt drives, which is more of a general overview on belt drives. I don't remember if I did send it, but I'm gonna resend it if I did. I just don't remember if I sent the video. Right. Either way, we are going to attempt this problem together. All right. Now belt drives is 5 marks in the exam. It is 5%. But understanding belt drives is important because just like epicyclic gears, you are going to carry that understanding into N5. Now we are going to cover belt drives extensively in N5, but of course it's always best that if a module or part thereof was covered in previous levels, that you carry that understanding with you into the higher level. Right, now let us look at the statement. So we can write down what we've been given here. I read as follows. The following is applicable to an open belt drive. Right, contact angle on the driving pulley is 160 degrees. Right, so the contact or the angle of contact. Now take note here. Right, you've been given the angle of contact. Right, so number one, they gave you the type of belt. They said they gave you the type of belt as well as the type of belt drive system. So you get two belt drive systems. You get one that is an open belt drive system, and you get one that is a closed belt drive system. Right, the video I'm going to send you. Right, I dive a bit deeper on that, as far as what an open belt drive system is and what a closed belt drive system is. Right, but the information for level 4 is more at a surface level. Right, we will dive even deeper when you get to N5. Right, anyway, you get two belt drive systems, open. One is open, one is closed. So in this case, they have told us that this is an open belt drive system. Right, and that the type of belt, the type of belt is a flat belt. Now, the type of belt being a flat belt, so you get two types essentially, or we look at two types. Flat belt, the cross-sectional area of which is one of, say, a rectangle. So meaningly, the cross-sectional area is length times breadth, essentially. Right, and then you get a V belt. Again, that type of belt alludes to the cross-sectional area of that belt. Now, for a not a cross belt, for a V belt, they normally just give you the cross-sectional area because it is quite awkward to have to calculate the cross-sectional area of a V belt. That's because of the way it's shaped. So it's shaped, right? If you look at it from a cross-section perspective, right, it is shaped as a trapezium. Right, so it is quite awkward to have to give students or candidates the measurements of the sides of the V belts in order for them to calculate or to be able to calculate the cross-sectional area of the V belt. So if you are going to use the area, they simply just give you the magnitude of the cross-sectional area of the V belt. Right, that is just for your information. Right, in this case, they've told us that this here is a flat belt, which means its cross-section is that of what is this? Is that of the rectangle, right? But in this case, you simply say thickness of the belt times the width. Right. Again, this is covered on the video that I sent you or that I'm going to send you. Right? But being told the type of belt, be it a flat or a V belt, alludes to its cross-sectional area or its cross-section. Are we clear?
Yes, sir.
Right. So when they give us the contact angle, so the angle of contact is 160 degrees. Right. Now with this one, we call the angle of wrap or the angle of contact theta. So theta here is 160 degrees. Now it is important to note that the angle of contact must always be in radians. So if it is given in degrees, you must convert it to radians. But we aren't going to do that here. We are going to do it on or when drafting our solutions. Right? But that is important to note that the angle of wrap must always be in radians, not degrees. So mainly if they've given you the angle of wrap or angle of contact in radians, then you use it exactly as it is. But if it is given in degrees, then you have to convert it to radians. Right. Rotational speed of the driving pulley is 600 revs per minute. Right. So we can call this. Now, as far as in terms of mechanical systems, right? With mechanical systems, regardless of which mechanical system you're looking at, be it belt drives, so pulleys, or gears, or chain drives, regardless of the mechanical system, right? The driver of that system, right, we take as the input, and then the driven of that system we take as the output. So that is to say that, seeing that we've been given the rotational frequency of the driving pulley or the driver pulley, we can denote that as N in, which means the rotational frequency of the input. Right? So N in is equal to 600 revs per minute. And then the diameter of the driver pulley or driving pulley, so this one we refer to as Dn, is equal to 650 millimeters, which you have to convert to meters. So that will be 0.65 meters. Belt mass is 0.35 kilograms per meter. Right. This kind of mass we refer to as M dash. M dash here is 0.35 kilograms per meter. Right. Normally, or the way we express the mass of the belt is per meter, or yeah, it's per meter length of the belt. Right. And this here helps in having to calculate the centrifugal force or the centrifugal tension if the centrifugal tension is of a considerable amount. The way you determine if the centrifugal tension is of a considerable amount is you look at the speed of the belt. If the speed of the belt exceeds 12 meters per second, then that tells you or that suggests that the centrifugal tension is of a considerable amount, hence you have to consider it. Right? Again, you look at the speed of the belt. If the speed of the belt exceeds or is greater than 12 meters per second, then you have to consider the centrifugal tension. Right? As far as a general perspective, that is how we look at it. Right? Otherwise, aside from that, if you've been told to consider centrifugal tension, then you must consider it, regardless of if the speed of the belt exceeds 12 meters per second or not. Am I making sense here?
Sir.
Hello?
Yes, sir.
All right. Right. So if you've been given this, that's another way that the examiner suggests that you should consider centrifugal tension, because you're only given this if you're going to consider centrifugal tension, because we only use this in having to calculate centrifugal tension. Right. Coefficient of friction 0,2. So this is 0,2. And then here we're also given the safe working stress in the belt, which is 4 megapascals. So the safe working stress, so that is, what is this? Having considered the factor of safety, right? The safe working stress, or the maximum stress that the belt can take, is 4 megapascals. So you can call this maximum stress, which is 4 megapascals, right? Now the stress, right, as you know, stress is synonymous with pressure, right? And pressure is measured in pascals. Hence, stress is measured in pascals as well. Now, the standard unit of measurement for stress or pressure is pascals. So if it's been given in anything else other than pascals, you have to convert it to pascals. So megapascals is times 10 to the 6, meaningly 1 megapascals is equal to 1 times 10 to the 6 pascals. So which means that 4 megapascals will be 4 times 10 to the 6 pascals. Right, and then we are given the belt thickness, which is 20 millimeters. Right, standard unit of measurement for thickness is meters. So you have to convert the 20 millimeters to meters. So this will be 0,02, right, meters. And then you're given the belt width, which is 155 millimeters. So the width is 0,155 meters. All right, that's all the information we've been given. All right. Now, before we go to the solution, having broken down what you've been given and what each quantity stands for, I want us to go back to this one. What's the safe working stress? Right. Remember I said the safe working stress alludes to the maximum tension or the maximum stress that the belt can take without even coming close to buckling, essentially. Right. So essentially, safe working stress can be taken as maximum stress. Now, the belt has two sides. One side is the tight side, the other side is the slack side. Now, this, right, the maximum stress alludes to how you can calculate the maximum tension which you get on the tight side. Right, so meaningly, you are able to use this information to calculate the maximum tension or the tight side tension of the belt. All right, so just keep that in mind. Now let's look at 11.1. So 11.1, they want us to calculate the centrifugal tension. So the centrifugal tension, which we denote as Tc, is equal to m dash times v squared. All right, so v stands for the speed of the belt. All right, so this will be equal to, so essentially we can say that this is equal to m dash times, now the speed of the belt. Right, the general formula for the speed of the belt is equal to pi dn. Right, now this formula you use exactly as it is if the thickness is not being considered. So essentially meaning if you haven't been given the thickness, then you use this formula exactly as it is. But if thickness has been given or if thickness has been considered, then you have to take into account the thickness of the belt. And the way you do that is, so here, let's say no thickness. But if thickness is considered, then V will then be pi times the effective diameter times N, which is the rotational frequency of the belt in revs per second. Right, so this one, thickness has been considered. So with this one, it's when there is no thickness, and then with this one is when thickness is considered. Instead of using the diameter of the pulley, you use its effective diameter, which essentially is the diameter of the pulley plus the thickness times N. Right, so DE stands for this here, D plus T. Are we clear? Right, so clearly here, thickness has been considered, which means you don't use this, instead you use this. Right, so here, so V is going to be equal to pi times, maybe let me do this. In fact, to make things maybe easy for us, perhaps we can do this instead. Right, first calculate V. So V is equal to pi times the effective diameter, which is the diameter of the pulley, plus the thickness times N. Now remember that the N is in revs per minute, right? In substituting it here, it must be in revs per second. Remember, the speed of the belt is in meters per second, not meters per minute. Hence, you have to convert the rotational frequency from revs per minute to revs per second. And the way you do that is by simply replacing minutes with its equivalence in seconds, which is 60. So here you have n divided by 60. Or you can simply say times n and then divide the whole thing by 60. Mathematically, it's the same thing. Right? And then now you calculate your V. This is pi times the diameter is 0.65. So 0.65 plus the thickness, which is 0.02 times n, which is n in, it's 600. Remember your brackets divided by 60. And what is this equal to? Right, so remember your parentheses here. And what is this equal to?
Zero comma 0.67 divided by 2.
Just make sure you got that correctly.
No, that's it. Quickly. Yes, quickly.
So this is 0.65 plus 0.02
21.
times 600 divided by 60.
I'm getting 21.049.
Right, I am getting the same. So it's 21, 049, remember, meters per second. Right. Now we have qualified why TC must be calculated. Remember, I said TC is considered if and only if, this is from a general perspective, only if the velocity or the speed of the belt exceeds 12 meters per second. Right? And this is almost double that, which means the centrifugal tension has to be considered because it affects the belt. Right? But again, like I said, sometimes your examiners, even when the speed of the belt is less than 12 meters per second, they ask you to calculate TC. So when you've been asked to calculate TC, you calculate TC regardless of if the principle has been followed or not. Right? So it means here, now you can simply substitute. This is 21,049 squared. And what is this equal to? Oh, sorry. I have to substitute this as well. M dash is 0.35. So what is this equal to?
155.066.
Okay, so that's fine. I'm gonna use 0.71.
I'm also getting 0.71, sir.
Yeah, so the previous speaker, their answer is correct as well. They probably just used the entire answer and just multiplied the entire answer by 0.35,
Oh, okay.
which is still fine. So they said, remember that we rounded this off. So instead of rounding this off, they probably just pressed squared on the answer and then multiplied by 0.35. Right. We don't care much, or your markers don't care much about the answer itself, but the understanding. So,
Yes.
but for perspective, I'm going to use this one. Then this is will be in newtons. I don't know if I'm making sense. Previous speaker, I think it's Danjan. Danjan, I was actually.
Yes, that's exactly what I did, sir. I just multiply from the answer and then I just square it. Sorry, I just square it from the answer and then without taking what was rounded off.
Yeah, no, that's totally fine. It's that approach is time saving as well. It's totally fine. Right. So this is your TC. So for 11.1, they just wanted us to calculate TC, and this would be the approach. Right. Now let's look at the next one. 11.2. Now they want us to calculate the tight side. All right. Remember, there's a number of ways in which you can calculate the tight side or the slack side for that matter. All right. It all depends on, based on what you've been given, which approach is convenient. And in this case, seeing that you've been given the maximum stress or the safe working stress, you can simply use that to calculate your tight side. Because remember that this correlates with the tight side only, not the slack side. And the way you do that is, like I said earlier, stress is synonymous with pressure. And as you know, pressure is equal to F over area, which means this stress can also be equal to F over area. But all you do is replace the force with the tight side, so T1. So T1 divided by the area of the belt. Right, which means to get T1, you simply cross multiply here, hence T1 will be equal to F max times the area. Now we already have the value of the maximum stress. As far as the cross-sectional area, you look at the type of belt. The belt is a flat belt, which means its area will be the thickness times the width. Now all you do is substitute. Maximum stress is 4 times 10 to the 6. So this will be 4 times 10 to the 6 pascals times the area, which is the thickness. The thickness is 0.02 times the width of the belt, which is 0.155. So that's 0.155. And then you punch all of this in your calculators. 4 times 10 to the 6 times 0.02 times 0.155. And what do you get?
I'm getting 12,400.
Can't be. Just recheck your answer there. This is what I'm getting.
The same says, it's just how I say it.
Oh, what did you say? Maybe I didn't hear you.
I said 12,400.
Oh, I thought you said 4,004. Okay.
No, I said 12.
Okay, yeah. So yeah, it's the same. Right. So that is your T1. And so, like I said, right, there's many ways in which you can calculate T1 and T2. You just look at what you've been given to decide on the best approach. And as far as this one, this is the more convenient approach. So now we look at 11.3. They say calculate the slack side tension. Now, the slack side tension, right? Based on what you've been given, there's only one way in which we can use to calculate, or we can approach having to calculate the slack side, right? And that's using the tension ratio. Now, the tension ratio, that's how, or the formula for calculating the tension ratio is based on the type of belt, meaning if the type of belt you're looking at is a flat belt or a V belt, right? The tension ratio for those belts is different, right? Again, you'll see this in the video I'm going to send you. I'm also going to send you the formula sheets that I formulated for belt drives for this level, right? So again, you consider the type of belt, right? And the type of belt will tell you how to express the tension ratio. That's number one. Number two, you then also consider if centrifugal tension has been considered, right? Now in this case, we're looking at a flat belt. Now a flat belt, its tension ratio looks like this. T1 over T2, that's the tension ratio, is equal to e to the exponent mu theta. Right? This is how we express the tension ratio for a flat belt. If TC hasn't been considered, but still looking at a flat belt, but now TC is being considered, that changes the expression for for the tension ratio. When considering TC, now you say T1 minus TC is equal to T2 minus TC is equal to, the right hand side remains the same. So TC being considered or not will only affect the left hand side. So with this one, this is where we've considered TC. Right? These formulas or these expressions are both on my formula sheet, and I've also explained them on the video I'm going to send you. All right. So obviously here, TC has been considered, right? 1, because essentially your examiner for this question has essentially told you to consider it by first giving you the mass of the belt per meter length of the belt, but also that was qualified by the speed of the belt exceeding 12 meters per second, right? So without a doubt, we should have considered TC here anyway. So this is the formula we use, right? Now if you look here, the only unknown here is T2. So from this expression, you have to make T2 the subject of the formula. We have T1, we have TC, we have the coefficient of friction, and we have theta. Right? Now theta has been given as 160 degrees. Remember that I said you have to express the angle of contact in terms of radians. And the way you do that, so converting from degrees to radians is simply to say, so your angle in degrees, you have to divide by 57,3. So which means the angle in degrees here is 160 degrees. We divide this by 57,3, and this will give us our theta in radians. So 160 divided by 57,3 gives us 2,792 radians. Are we getting the same thing?
Yes, sir.
Yes, sir.
Right. So just make sure you look out for this one. Right. The angle of rep, so your theta must always be expressed in radians.
Right.
And if you have to convert it, this is how you do the conversion. This is the simplest way of doing it. Right. So now let's substitute. Right. T1, we calculated T1 and it's 12.4. So this is 12,400 minus TC, which we calculated and got the 155. The 155,071 divided by T2, which is what you're looking for, minus TC, which is 155,071, is equal to e to the exponent mu, which in this case is 0,2. So this would be 0,2 times the angle of rep in radians, which is 2,792. Right? Then now how you go about this mathematically doesn't really matter, right? Because essentially the Meccano, it ended at this point. So this is where you show your understanding as far as what you do when you're looking at a flat belt, or the tension ratio of a flat belt, having to consider the centrifugal tension. So the understanding ends here. Once you substitute, or once you've substituted, right, Meccano is essentially ended. It's now just how good you are with your maths. Right, so that is to say that you can either follow my approach mathematically, or you can follow yours if you're comfortable with yours, or if yours is better. Right. For now, though, I'm going to break this down step by step. So, meaningly, I'm going to take this as it is. Right, so first, solve the numerator. The numerator is 12,400 minus the 155,071, and there I get 12244,929 divided by the denominator remains the same. So this goes down exactly as it is. The right hand side is e to the exponent 0,2 times 2,792. So this is 1,748. Right. Then from here, I cross multiply. When I cross multiply, I will have the 1,748 into this, which is equal to, and on the right hand side, this is what I'll have. Right. Remember I said how you continue with this mathematically will be up to you. Right. But I'm just gonna continue breaking it down step by step. And then remember we're looking for T2, so we're trying to make T2 the subject of the formula, which means now we have to get rid of this. The way you do that is by dividing by its both sides. So you divide both sides by the 1,748, 1,748. Obviously, that cancels. And then on this side, you have T2 minus the 155,071 is equal to the right hand side is still this. Right. Again, remember you're trying to make T2 the subject. So now you can simply just take this term to that side, right, which will then change the sign. So seeing that it is positive on this side, when you transpose it, it becomes positive. Therefore, meaning T2 would be equal to this plus the 155,071, right? And then now you can simply say the 12244,929 divided by 1,748, all of that plus 155,071, and here I get 7160,179 newtons. So your answer must be around this.
Correct, sir.
Yes. And that becomes your T2. Any questions on this one?
I think it's clear as long as you get your questions your formula correct.
Yeah.
Because it's a substitution.
Yes, that is correct. Right. As long as you get this correctly, you should be fine. That is correct. Right. So that's 11.3. Let's look at 11.4. Now they want the power transmitted. Right. Now all of your mechanical systems. Okay, maybe let me not say your mechanical systems. Your mechanical drives. So you get essentially 3 mechanical drives. You have your belt drive. Right, you have your belt drives, which is the one we're looking at, but you also have gear drives as well as chain drives. All of your mechanical drives, right, all they do is they transmit power, right, or the common function for mechanical drives is to transmit power, right? Hence, regardless of the mechanical drive you're looking at, the approach that you take, right, or in terms of how you use your power from a perspective of efficiency is going to be the same, meaning the efficiency, mechanical efficiency, will always be the output power divided by the input power times 100. Right. So this we refer to as the mechanical efficiency, which will remain the same regardless of the mechanical drive. Right. So that is just something to take note of. Right. So here they want us to calculate the power transmitted. Right. So as far as the transmitted power, this is 11.4. Right. Now if your drive is 100% efficient, right, your transmitted power will be equal to the input power, right? However, if your system is not 100% efficient, then the power being transmitted essentially is the output power, right? Because remember, it is the output power or the power being transmitted you will get on the output shaft. Hence, we refer to the power being transmitted as the output power. And so you can essentially refer to this as P out for output power. For belt drive specifically, we use the effective tension, multiply that by the speed of the belt. Now, effective tension, now if you remember from bearings, I did explain there that you get dynamic tension and you get static tension. The static tension we refer to as the installation tension, which is what we use in bearings. For belt drives, because power is being transmitted, we use the dynamic tension, which we refer to as the effective tension. And the way you calculate effective tension is T1 minus T2, so times the V. At this point, you already have T1, you have T2, and you have the V. So T1 was 12,400. So this is 12,400 minus T2, which you just calculated, 7160,179 times V, which we got 21,049. Right, and then this 12,400 minus the 7160,179 times 21,049. Here I get, so this is too large of a number, hence I use engineering notation, and I get 110,293 kilowatts. So because this is too large of a number, I made use of engineering notation. So after having gotten the answer you get, you just press engineering notation.
Correct, sir. It's the same.
Yes. All right, so that's how you calculate your output power, or your power being transmitted. Right. Then the last one, 11.5, calculate the modal power required if the drive has an efficiency of 80%. It's very important that if they want the modal power, that they give you the efficiency. Because like I said, if your system, which is unlikely, but if your system is 100% efficient, then the input will be the same as the output, or vice versa. So seeing that they want the motor power, which is the input power, that suggests that your system is not 100% efficient. Instead, it is 80% efficient. Right, and like I said, to calculate mechanical efficiency, so this is 11.5. Right, mechanical efficiency is equal to the output power divided by the input power times 100. Right, now this is 80%. Right, so to get rid of this, you simply divide both sides by 100. Hence, this will be 0.8 is equal to output power, which is 110.293 kilowatts, divided by the input power. And then when making the input power the subject of the formula, it means this will be 110.293 kilowatts divided by the efficiency 0.8. Right? So, and then you see 110.293, you divide that by 0.8, you get 137.866 kilowatts. Well, approximately.
That's correct, sir.
Yes. Right. So that is how you would approach such a problem. Right. The key thing with belt drives is, like I said, to know or to take note of the type of belt being used, as well as the type of belt drive system. Right. Type of belt drive system will either be an open belt drive system or a cross belt drive system. If the type of belt is a flat belt, that alludes to how you are going to calculate or how you are going to express the tension ratio. Similarly with a V belt. Right, so with the V belt, the way you express your tension ratio, so the left hand side will still be T1 over T2 is equal to E to the exponent mu theta divided by sine beta. Now the angle beta is known as half V groove angle. Right, I explained this in the video. Right, but I'm just saying for interest sake that beta stands for half V groove angle. Now the difference between the two, theta and beta, right? Theta must only be expressed in radians. Beta on the other side must be in degrees. So you do not convert the half the V groove angle. Do not convert it to radians. You leave it in degrees. And the reason for that is because the reason why we even convert the angle of wrap to radians is because how the angle of wrap is formed is based on rotational motion. Now you get different types of motion. You get linear motion, also known as translation, and then you get rotational motion, which is also known as angular motion. And then, of course, other elements. You find that when they move in a manner that the components or elements or link translates as well as rotates. right? But the two main types of motion is linear or translational motion, or rotational or angular motion. Now, the reason why that this theta has to be expressed in radians because the way you look at the angle of rep is from a angular motion perspective, whereas beta, which is half the vehicle of angle, you look at from a linear perspective. That is why beta remains in degrees and theta is converted to radians. The reason is the type of motion. Any more questions on belt drives? This is the one problem where I felt like it covered more or less everything as far as belt drives in terms of the quantities that we need to calculate. Right. That is why I chose this problem. Any questions on belt drives?
I
So
see, sir, on the question on the formula sheet, they're giving us. I'm not sure if it's the correct one. Especially for that one with the sign, it's a T1 over T2. Oh, sorry, T1 minus TC over T2 minus TC is equal to E. Oh, okay.
Yes.
That is now okay. The
Right.
inverse of.
Yes. So because we don't have cosec on our calculators, we rely
Okay.
on. Right. But remember that when it is written as cosec beta, it is written as e to the exponent mu theta times cosec beta. But because cosec is equal to 1 over sine beta, that is how you get this.
Oh, okay. Okay. Thank you.
Yes. Right. Any more questions?
no, say, look, say just the very last question. Just now maybe your advice when it comes to the formulas. I always struggle. Say for example, now when we look at the Bernoulli's principle, for example,
Yes.
that formula Z1 plus P1 over rho times G and then. But if you look at the question paper itself on the formula sheet, that 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 formula doesn't appear. So, in, it- so what do you do in situations like that? Do you have to memorize some of these formulas in
No.
order for you to be able to?
No.
Yeah.
You don't have to. So with Bernoulli's different variations, Bernoulli's equations, right? There's three variations, but it does not matter which one you use.
Oh, okay.
It does not matter. So if you're someone who perhaps struggles with memorizing the three variations, you can simply use the one that you've been given in the formula sheet.
In the formula sheet.
Yeah.
Oh,
And then you'll simply manipulate it in a manner that will give you what you're looking for.
okay. Okay.
Like for instance, number 47 here, you can use number 47 exactly as it is. Right. So it's P1. Now, obviously, the way it's written, whoever was formulating this formula sheet made a mistake here. Right. Because the P1 doesn't necessarily look like a P1 because the one is supposed to be a subscript
Yes.
Just look out for those mistakes as well.
Yeah.
But the formula reads P1 over rho, which is the density, plus V1 squared over 2, plus, what is this, GH1.
One.
Yes. And then the right hand side is expressed the same. It's just that it is the outlet.
Yeah.
Right, so you can use this and just manipulate it however you need to get what you're looking for.
Okay.
Right, so it doesn't matter which variation of Bernoulli's equation you use.
Okay.
Yes.
So did I hear you correctly? You said this is the very last session now in this before the test.
Yes, because I have to give you time to study on your own. You remember, you're only left with Wednesday and Thursday,
Yes, sir.
but I'll still be answering questions in the
Oh,
group.
okay.
And
Okay.
then if maybe the question that's been raised warrants me having to record a video, then I'll record a video.
Okay.
Yes.
Okay. No, thank you, sir.
Right. So that is why even this session, we've never had a session this long.
Yes.
I want to make sure I answer all your questions that you have, like right now.
Mm.
But probably most of you will have more questions tomorrow.
Yes.
Understand work and things.
Yes.
Yeah. Yeah, I'll still be available. But obviously, it's not going to be convenient to have a 2 hour session again tomorrow because you need to have time to study on your own.
Yes, sir.
Yeah.
Okay.
Right. Any more questions?
No, I'm okay on my side, sir.
Right.
I think I just want to thank you, Mnasa, on my side. Having to have a session this long, I think it was just something that you extra did it on your side, because we normally have an hour session and then having to double up your time. I really appreciate that, and I think we've got to like learn a lot. So I really appreciate that. Thank you so much.
It was my pleasure. As far as tutoring, I don't necessarily tutor the way, well, in the conventional way that it should be done, because I do understand engineering is not the same as what is other qualifications. So it isn't, it's not really about the money. I just want to give the best of myself to the students as far as possible. You see, it's about you guys, making sure that you guys, um, I give you whatever that I can to assist you in your journey in having to do this difficult qualification.
Yeah, we really appreciate it, sir. Yeah.
No, man. Thank you very much. It's my pleasure. Right. I guess we are done here, so I'm gonna stop recording. I will upload this on my YouTube channel for